Hello everyone. Today we're going to talk about periodic functions, and the focus here is going to be to identify the fundamental period of each function. So try to do these exercises on your own, and then pause the video, try to do it on your own, and then see if you got the right answer. I'm going to start writing the solutions. For part A, all you really need to know is that cosine sine, both of them, okay, whatever the scaling factor of t is, that is going to be its omega, and the period t is equal to 2 pi over omega for sine and cosine. So in part A, we have t1 equals to 2 pi divided by 2 pi, which equals 1. And for the cosine, we're going to have 2 pi divided by 5. The second step, that if you only had one term here, then whatever t1 is, then that would be your period. But because we have two terms of sine and cosine, we need to find their fundamental period. To do so, we need to see if there even is a fundamental period. An easy way to check that is you do t1 divided by t2, and you see if it is a rational number. In this case, it'll be 1 divided by 2 pi over 5, which is going to be equal to 5 over 2 pi. Now, because this number is irrational, then the function is not periodic. So x of t is not periodic, and so there's not going to be a fundamental period. Now for part B, I'm just going to erase this. For part B, we have 1, and for all constants there is no period. The period is pretty much 0. You don't have to consider the constants when calculating the period. For cosine, the cosine term over here, we have 2 pi, t1 equals 2 pi divided by 2. So the period is pi. And for t2, we have e to the j5t. Now remember Euler's formula. You actually need to write this out. So e to the j5t is equal to cos 5t plus sine 5t. These two have the same period, so we could just write it as 1. So t2 is going to be 2 pi over 5. Now we do our check. t1 divided by t2 is equal to pi divided by 2 pi over 5. So this is going to be equal to 5 over 2. Because this is a rational number, then the function x of t is periodic, and the fundamental period t0, we have to find it. So it's going to be equal to the LCM, least common factor, of t1 and t2. So t1 we know is equal to pi, so we could write pi. t2 is 2 pi over 5. Now the way I like to do this is I like to just keep adding pi, or keep just multiplying the term until you find a common factor. So here, for example, for t1, we're going to have pi, then we're going to have 2 pi, then we're going to have 3 pi. We just keep adding pi. And for t2, we're going to do 2 pi over 5 plus 2 pi over 5. The next one is going to be 4 pi over 5. Then we're going to have 6 pi over 5, 8 pi over 5, and then finally we're going to have 10 pi over 5, and this is just equal to 2 pi. So these terms are alike right here. This is the least common factor they have. So the fundamental period is going to be equal to 2 pi in this case. Now, let's solve part C. Okay, for the last part, we have sine, absolute value of sine pi t. So, to find the period here, we're just going to do what we always did and just say that t is equal to 2 pi over pi, which is equal to 2. If this was sine pi t, I would leave my answer like this, but it's better to check with the graph because we have an absolute value. So I'm just going to graph the function here and double check if the absolute value changes anything or not. So 0, and normally it would be pi over 2, and we would do pi and 3 pi over 2. Right, we could keep extending this, maybe like 3 pi over 2, and let's go with 2 pi. Now, because we actually don't have sine of t, but we have sine pi t, remember from the first episode that everything is scaled, so we divide everything by pi. So here we're going to have 1 over 2, 1, 3 over 2, and 2 pi, and 2. So here we have it like this, then it goes to 0, then it goes to -1, back to 0. Now, because we have absolute value, this section here is just going to be eliminated and is going to turn positive. So something like this, which, if we look graphically, we see that we went from 1 over 2 to 3 over 2. And the way you get from 1 over 2 to 3 over 2 is 1 over 2 plus x equals 3 over 2. So if we do times 2, we get 1 plus 2x equals 3. And x is equal to 2 over 2, which is 1. So the period is actually going to be equal to 1 in this case. Because of the absolute value, this original period of 2 gets divided by 2 again. So it is twice as short because of the absolute value, which makes sense, right? Because you could see it graphically that the next time we get to 1 would have been at 2 pi plus pi over 2. But because of the absolute value, the negative section goes into the positive, and that shortens the period by half. So our period is going to be 1, and the fundamental period, because it's the only period, or the only factor that we have here, then the fundamental period is just going to be 1. And yeah, that's it for periodic functions. Okay guys, for the last part of this video, we're going to talk about even and odd functions. So all you need to know for this course when it comes to even and odd functions is that, I'm going to write it down here real quick. So for an even function, we have the property x of t equals x of negative t. And then for odd functions, you have the property x of t equals negative x of negative t. Okay? And you also need to know the formula, because sometimes you have questions with proofs like this one, where you have to show, you have to prove something using this identity that an even function is equal, so for example x of t is equal to x of t plus x negative t, and you could do all this 1 over 2. And then for odd functions, it's the same thing, but we plug the odd function property, so we do x of t minus x of negative t. So that's pretty much it. With that, we can solve the first couple problems, A, B, C, and D. Okay, so for part A through D, we have to determine if the function is even or odd. So try to do this by yourself, and then I'm gonna walk you through the solution. For part A, we have x of t equals t cubed. So let's plug in x of negative t, and we get negative t cubed, which is equal to negative t cubed. Now remember that t cubed is x of t, so this is just equal to negative x of t. So since we have x of negative t equals negative x of t, we could just divide both sides by negative 1, and we get negative x of negative t is equal to x of t. And so this is the definition of odd. So we know that part A is an odd function. So I'm just going to write odd, therefore odd. Part B, we have t cubed, the absolute value of t. So again, same thing, negative t. And we get negative t cubed. And now we have absolute value of negative t. But this is just going to be equal to negative t cubed, absolute value of t, because the negative goes away, right? So again, this is just equal to, right here, this is x of t, so we could just say that this is equal to negative x of t, and so we have the same thing, negative x of negative t equals x of t. So this is also an odd function. Now we have absolute value of t cubed. For every problem, we just do the same thing. We plug in x of negative t to test. So negative t cubed. This is equal to absolute value of negative t cubed, which is equal to absolute value of t cubed. So x of negative t is equal to x of t. So we have x of t equals to x of negative t. So this one, part C, is even function. Now part D is something that'll be more applicable later on. For cos and sine, one thing you need to know about cos is whenever you draw your unit circle, even for sine. Oops, let's do it like this. Okay, it's not perfect, it's an ellipse, but whatever. If you have some angle theta and you plug in negative, you get negative theta. You can see by the symmetry here that cos, because it gives us the x value, it's going to be the same whenever it's negative. And for sine, we should just see that we get the negative value. So, for the first one, cos, and for part D, we have x of negative t equals to cos negative 2 pi t sine negative 2 pi t, which is just equal to negative cos 2 pi t sine 2 pi t. The reason we have this negative is because negative sine of negative 2 pi t is just equal, sine of negative 2 pi t is equal to negative sine of 2 pi t. That makes sense. Okay, we had the negative inside here, we could just bring it out. And for cos, we could just put the negative inside the parentheses and remove it. It's the same thing. So here we have this expression, which from the beginning, this was just x of t. So this is just equal to negative x of t. And again, you can see just from the first part A that whenever you have negative x of t at the end, it just becomes odd. So I'm just going to say that therefore x of t is odd. It's an odd function. Okay, for the last part, we have to prove that the integral from negative a to a of a function x of t dt is equal to 0 if x of t is an odd function. Now you may know this from calculus. Some schools like to test on that theory. I personally did not get any questions on even or odd functions for calculus, but it's pretty simple. You could just see it graphically. You could also prove it mathematically using the properties over here. But if you look at it graphically, let's say you have a function x of t that looks like this, right? And so the integral until a is going to be this area under the graph, right? But if you have an odd function, that means that you probably have this part and you also have this like an even symmetry over here, where this is negative a. So if you take the integral from negative a to a, you have, because of the symmetry, you will have some area a here, and you'll have that same area but negative. So the integral is just going to cancel them out, and it'll be equal to 0. This is proved graphically. Sometimes you have to use the property to prove it mathematically, but I won't be doing this for this video, so just do it as an exercise.